In the previous lecture, we treated O by P as a vector space. In the same lecture, we described certain positions, we positioned, say, rho, as an element of this vector space, wherein the elements of rho is some element x sub I, y sub I, such that x sub I is an element of O, which is equivalent or can be defined to be L, or language L, which is precisely the Queenstown operation over our alphabet A, where A is our alphabet. A, B, C, and the dot X, Y, Z. So we discussed in the previous lecture. And also y is also an element of this A star. A star. And O is, it's not really equivalent to a language, but rather is a subset, a proper subset. And in the same vein, MathCal P is also a subset. But of course not equal to this entire thing. Of course, y is some element of this such that it describes the preference or the dynamic of a person, and then y and the x now describes the orientation of a person, or actually this appearance, and this is the orientation. Okay. And not only do we express it in terms of a rectangular array, but as combinations of two vectors. So we have one vector or one extreme, or we have one vector that belongs in one extreme, and we have another vector that belongs in another extreme. And we can express a switch as a sort of linear combination of these two extremes. So say we have our system here, and then we have infinity plus infinity p minus infinity p plus infinity o minus infinity o. And we have our extremes here, and then we have some limit, which is some halfway point, which I will call alpha on A. And this is minus A, and this is A in the up direction, and this is minus A in this direction. And so from here we say that beyond any vectors that lie in this interval, which is A included plus infinity B not included, any vector that lies in here is an extremely dominant person, and would be for that, and before A, or any vector that lies within this interval, 0 up to A, both included, for this closed interval, is a dominant but not very dominant person, so a minimally dominant person. And then a vector that lies precisely on A, or the dot product rather of the vector with respect to this minus P plus P axis, if that dot product of the vector lies directly on A, or its projection is precisely on A, then we say that that vector is adequately or balanced, is a balanced dominant, right? So again, we can express other vectors here as combinations of certain vectors that lie within these guys. So switch vectors, or vectors describing switch people, can be thought of as a sort of combination. So here, now we can just combine these two vectors by using the parallelogram rule to get a new vector. So, right. It's just in the same place here, roughly. So we just use the parallelogram now to derive the actual vector, and the final vector, or the resultant vector that we get from taking the linear combinations of these two vectors, is the vector that we put on the question. So equally, if we have a vector, we can sort of break it down into principal components, or an arbitrary sort of combination, a linear combination of various other vectors these extremes. So we now state as a sort of a lemma. I'll call this lemma 1. You guys see this? Yeah. Lemma 1. Lemma 1. Any position vector which I will call ket v can be broken down into a linear combination of two or more position vectors. That lie in any interval in our system. Okay. So this is our lemma 1. Now the proof for this is that, okay, so given a linear combination of these guys, we just need to prove that the Wronskian of such linear combinations is non-zero. And the Wronskian matrix is basically just it's a matrix composed of these vectors. And if we take the determinant of the Wronskian matrix, and the Wronskian matrix is non-zero, then the vectors on the question are linearly independent, and that they can compose P here. So that's what I'm not gonna write it out. You guys can work out as an exercise. So again, any position vector V can be broken down into a linear combination of two or more position vectors, stuff like V, that lie in any interval in our system. So if V is something that's extremely dominant, we can sort of break it down into two predominantly dominant vectors. So for example, and just it's arbitrary because there's no really precise way of saying it, because we know that operations are actually very arbitrary. Like let's say 3. What can we say about 3? Well, we can break it. Oh, not 3. Let's say 8. What can we say about 8? We can say that we can break down 8 into the operation 4 plus 4. But at the same time, we know that this is 6 plus 2, so we can break it down into 6 plus 2. And we know that this is actually 4 times 4, 4.4. We can do that. And we also notice that we can break down these guys and say that this is 2 plus 2, 2 plus 2. And we know that this is actually 2 cubed. 2 times 2 times 2 times 2. So this is 2 cubed. In the same way that we can break a number or a composite number into various factors and operations on two smaller numbers, we can do the same thing to our position vector. So we can break down a position vector into two component vectors, we can say, that can either lie in one interval or in two or more intervals. So I'll just list it down here, our intervals. Our intervals is from 0 up to plus t, calculated 0 up to minus infinity p, 0 up to plus infinity o, 0 up to minus infinity o. Okay, so these are our main 4 intervals in the system that I created. Again, arbitrary thing, but we're going to stick with the system that I constructed in the first lecture. So, yeah, suppose that one vector or one component, actually, let's say that one long vector or big vector that can be broken down, or composite vector, which we can break down into small vectors, lies within, let's say, this interval. Let's say that P is an element of this interval. Okay. And P is a large vector. And let's say that P is beyond our defined median. P is bigger than A, wherein A is our median, or the thing we split to determine minimal and maximal dominant equal. Okay, so first let's say that it's a large vector and then B is greater than A. So what we can do is break down P as a sum of two vectors A and B, two position vectors A and B, such that A and B can be, as long as A and B are non-zero, so such that A and B, or rather the norm of these guys and the norm of B are non-zero, or not negative, they're and also non-zero, of course. We can't have zero distance here. We want it to lie in an interval that's greater than A. And we also want to state that the norm of their sum is greater than A. So if we add these guys together, we get P. Because P is greater than A and P is a large vector, well, it doesn't matter if it's a large vector, we just want to say that it's larger than A. It must hold that its components, A and B, must be greater than A. So let's say it's something like, let's define our threshold or our median A to be, let's say 4. 4 in this interval. So ignore the other intervals for now. And suppose that our P component of, so let's say our P function, which I will define to be the P component, so it gets our vector and spits out the P component of P. Let's say its P component is 5. Okay. Now we can break down 5. Okay, I'll define now A2, B4. Now we can split the P of our position vector into two vectors, or the position or the P function of A and B, basically. And let's say that A and B are two parts of 5, non-zero, but not necessarily greater than 4. Okay. But we can make it greater than 4. So there are two options here. If we want to say that it is non-zero or not negative, we can just put these two. We can just put P of A to be equal to P of B. We can just put P of A to be equal to 2, and this is 1, 3. So that our P component, or the addition of these two, gives us 5, which is the same thing, and it checks out. Or if you guys want to go with the it's greater than 4 route, we can say that it is something like 4.5, right? 4.5 and 0.15. I know the other one's less than 4, but there's really no other options to say that it's greater than A, and then we would get 5. So if our threshold was lower than this, it'd be easier to actually say that. Like say A is 2, then it would be easier to pick two sort of P components of two vectors that gives us this, or that gives us 5. So we can put, so if we want one of these values to be greater than 4, we put this function of A to be equal to, say, 4.15, or 4.5, it's 4.5. And then we put the other one, A, to be equal to 0.5. So that when we add these guys, we get 5. We can do that. That's it. We want this to be greater than 4. And now this actually satisfies half of the second condition, and it satisfies the first condition also, which states that it's not negative. Now, what we want to do now is define these two vectors, these A and B, that composes P, to be what is known as the inspiration for P. Inspiration. we'll call it the inspiration or predecessor of P. Okay, now definition 5. Definition 5. Let P, a row, be a position vector that can be broken down into a linear combination of two vectors vector A and vector B. Okay. Such that A and B, or rather the norm of A plus B, is greater than some predefined threshold or median in any interval in O cross B. A and B, vectors A and B are the inspirations of vector B. Are the inspirations of B. So that's inspiration. Now, I went actually into a tangent here. This is not what we're actually going to discuss, but it's good to lay this definition down, 5. And I'll discuss about linearity. Now, when both of these guys do not equal B, they are said to be linearly linearly dependent. Or maybe it's the other way around. When we can sum them up to a value, we say they are linearly dependent. And if they cannot equal some vector, then they are linearly independent. You guys tell me on that one, if I'm wrong or correct there. Okay, now let's go to the actual meat of today's lecture. And the meat of today's lecture is what is known as a linear transformation. So we're gonna start talking about switching positions. Suppose you're top and you want to be a bottom at some time frame or during some time frame. The best way to describe this change is via a matrix. So our identity matrix, or the matrix that does nothing, is 1, 0, 0, 1. And this just gives us a regular I hat and j hat components, which are just basically our basis for our system, or the most basic basis for our system. And then we can change it into this over here, this new vector, new system, A, B, C, B, D, where AC is the coordinate for I hat and BD is the coordinate for J hat. And so from there on, any position vector inside this system, or composed here in this, say this axis over here, gets squished or morphed or changed. Their position is changed. So if we have a vector over here, if A, C, and B, D switches all the vectors in this region onto this region, after applying the transform on the entire system, we would get something like this, or like this. And so from there on out, we can say that this position vector has effectively switched positions over here. However, if a position wants to become a switch, it splits itself into two vectors that lies in both intervals or both extremes. So it has successfully switched. Now every linear transformation is some function that takes all vectors in the vector space, in our case O cross D, and spits out a new vector that's a part of the linear transform of everything. So again, we'll make the assumption that O cross D is a vector space. A switch in position is a linear transformation. So this is definition 6. Definition 6. Okay, let be a vector space. Be a vector space. A switching of positions over O cross B is a linear transform. Which we will call S. Where S is not a person space, but rather this is a linear transform that maps O cross B onto itself. Okay. So it's still the same thing. It maps two-dimensional vectors onto another two-dimensional vector inside this space. So it stays the same thing. It doesn't squash space or anything. If a vector, if a matrix, say M, maps a certain space, A cross A, onto A, this means that this over here is a something like, you can think of it as a 3x1 matrix. Yeah, you can think of it as a 3x1 matrix that squashes this two-dimensional space onto one-dimensional space. Something like A, B, C. No commas. Likewise, something like A, B, C, like this, like a vector. This is a vector. It's not really a matrix. So it's just like this. Something like this squashes space into one-dimensional space. But that's a different case. Over here, we have a 2x2 matrix because it stays the same. And since it's 2x2, that means our dimensions stay the same way. So therefore, it's just a sort of stretching or squishing of space. Not really bending because it's linear. We want things to be straight. And I know it's a bit counterintuitive. We have a bunch of not straight people or stuff, and then we sort of change them in a straight way. But this is math. It's not really. It doesn't really. It's not really. It doesn't care if you are like this or like that. It doesn't care if you're gay, if you're bisexual, if you're pansexual. It doesn't care. Neither does logic too. Okay, so a switching of positions over O cross B is a linear transformation S that maps O by B to itself. So and fixes a vector V that's inside of O cross B onto a V2 that's also a of O by B. A V2 that's also an element of O by B. This is fixed by S. And so now this V2 is the image of V under this S. So the image under S of V is V2, which is an element of O cross B. But V2 cannot be V1 unless S is an identity matrix. So V cannot equal to V2 unless S is an identity matrix. Identity matrix. Okay. So enough about showing it in forms of maps. The most common way of showing a linear transformation or representing a linear transform is a matrix. As I said a while ago, we change our original system that's composed of unit vectors 1, 0, and 0, 1 into some other system that changes the position basically, or the attributes of a certain position. So suppose that a certain position vector is gender fluid and is predominant or primarily a top. And then suddenly, after some thinking, or their emotions start dictating that they are in fact a submissive and they are a just gay, regular gay. Or actually, since we're talking in terms of appearance and orientation, let's say let's say that the person is no, actually we're talking about orientation and sort of, or no, appearance and their sort of dynamic. Okay, let's say that. So a person wants to be feminine and submissive at first, and then suddenly starts saying, "Hey, I want to grind. Let's get that grind set." So the linear transform associated with that change is basically something that flips all vectors in this region onto this region over here. So okay, I'll draw it down. So let's say that the person used to be here, or is described using this vector. So this is O, and this is B, and then we're gonna use the thing that I assumed in the first lecture. Now if the person wants to get the grind on and turn into a really strong, buff, masculine, and pop, what he's gonna do is lay down the estrogen, lay down the HRT, start taking more testosterone, start being manly, and then switch over here. Or maybe for exercising, stuff like that. And so the matrix associated with moving this over here, or every vector here, likewise would move vectors over here, onto this region. So if this is over here, and we have our regular basis vectors here, I suppose the linear transform, or the effective action S, would be something akin to, well, first it was over here, it's composed of these vectors, but gone over here, and then move there. So what it's going to do is sort of flip it around. So what it's going to do is make this negative so that it flips over here. So it's something like minus 1, 0, 0, minus 1. And then applying that on this vector should, in theory, flip it on the other side. It would stay the same. And if the dot product of this vector, the resulting vector, is greater than our threshold A, then it is officially part of a maximum interval. So it is maximally masculine and popish, or dominant. So that's one. And likewise, if a very buff and manly guy wants to start acting and dressing like a girl, like a sissy, or stuff like that, start being a femboy and then start being a sort of submissive person, we would do the same thing. So let's have our O and B here, and then our vector is over here. Beyond the threshold A, and then we have our regular stuff I hat and J hat. What we want to do this time is still negate it, make it negative, such that this positive over here flips over here, right? So it goes from here up to here. So it's still a minus 1, 0, 0, minus 1 matrix. This is not an identity matrix because it flips space. It may look like an identity matrix or identity switching positions over this vector space, but rather it's still something because it moves the vectors from this region onto this region. And vectors from this region are moved onto this region. So it's not identity. Now what's interesting is that there are matrices that are invertible. So that means we can sort of do the reverse of it. So a matrix A multiplied or composed with its inverse gives us the identity matrix 1. Which is where 1 would define 1 to be 1, 0, 0, 1. So any matrix A composed with its inverse gives us just the identity matrix, like doing nothing. So going back to our example a while ago, their system, O cross B, and we have a vector over here. Applying A, say it's gonna move it over here. And then say A inverse is moving this around here. So basically, doing A inverse and then doing A again does nothing to it. So let's say it goes here first, and then applying the inverse A goes here. So when we read matrices, it's non-commutative. So this over here goes first, right to left. You have to read right to left compared to regular stuff like 2 plus 1 times 3. We have to read this from left to right. But when it comes to transforms or functions, we read from right to left. So this is not equal to a to the minus 1 times a. Or rather, applying a first and then a to the minus 1. It's not the same. Though these guys can actually be the same in the contents wherein they both equal the identity matrix. But regularly, if we have two separate transforms, two different matrices, A, B, it's not the same as applying A then B. So this is not the same as this. But this is the same. Only inverses or matrices going with its inverse or paired with its inverse only is the only sort of commutative things with this. So out of this, we can sort of form a group. Invertible matrices, just one. We can form a group out of this, and actually we can form a group out of A, B here, as long as A and B has their inverses. But that group would be non-commutative or non-abelian. If we want to construct an abelian group out of these switching positions, then it would be something like this. It has to be only A and its inverse, and then our identity matrix. That would be an abelian group under multiplication or composition, of course. Okay, so now let's think in a more general sense and suppose that we have a person space. So we have a collection of, let's say we have a person space. So we have two person spaces S1 and S2. So we have two person spaces S1 and S2, where S1 and S2 is a sort of is a set of people or position states P equipped with its topology. So that's one. So it's our space. S1 and S2 could be O by P, or it's some other interval that describes people. Now we define a linear transformation, or a more general form, to be a morphism or a homeomorphism between these two topological spaces. So when we define a homeomorphism with these two, or if there's a homeomorphism between S1 and S2, which can be sort of thought as a movement or a switching of positions, then we say that S1 and S2 are locally homeomorphic. That means we can map subsets of this onto subsets of this and vice versa. So if there exists an M that maps S1 to S2 and I'll say it maps S1 to S2 and maps S2 onto S1. S2 and S1 are locally homeomorphic, or just generally homeomorphic. Okay. S1 and S2 are homeomorphic if there exists an M that does these two inverse maps. And if we assume that S2 is a subset of Rn, if S2 is Rn, and there exists this map that maps a subset A, an abelian block, a subset of S1 onto Rn, or subsets of Rn, then we can say that S1 is a manifold. But that's something that's not related. It's not related to the study. I'm just gonna say that if it's sort of, if we have points, or if we have persons within S1 that has neighborhoods which we can map onto subsets of Rn, then that person space can be classified as a manifold already. Now. I can say, or we could talk about switching position as functions, but that's already under mapping. And so, that's the gist of our lesson today. Basically, they're basically just maps. They move one thing from another, or they change one thing to another. That's what it does through a function. Wherein that function rule is our matrix. So now, in general, on L, a linear transform transforms one vector space onto itself, or maps V onto itself. Wherein L, or actually a vector V in V is mapped onto some L by V, which is still inside of V. So for all V in the vector space, so our linear transform is equal to this generalization, such that for all V inside V, V is mapped onto this linear transform times V. So there. And then V is, or L is defined as some n by n matrix. A dot 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 A n dot 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 A and 1 and then 1 n dot 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 A n n. Okay. Wherein n here is the sort of the dimension of our vector space, or the rank of our vector space. And the rank of a vector space is just the dimensions, the amount of components we need to describe a vector inside it. So that's actually it for the lecture today. So since we've talked about linear transforms now, it would be wise to talk about eigenvalues and eigenvectors, right? You guys know that. And the eigenvector eigenvalue equation, which is basically given a linear transform A and then a eigenvector V, there is it's equivalent to some lambda times V. Wherein lambda here is our eigenvalue and then vector V is our eigenvector. And this basically describes or tells us, this equation tells us what vectors are actually that don't change. So people within the system that don't change their positions when we apply a matrix. And there's a small trick I want to teach you guys in computing lambda here before finding V. Just given A. It's a very neat trick. It's made by Turbo One Brown. And I'll discuss that in the next video, where when we talk about transforms, eigenpositions and eigenvalues.